I made a comment in my previous talk that the free surface multiple algorithm and the internal multiple attenuation algorithm not only do not care about subsurface information, they don't care what Earth model type you have. They don't care if the Earth is one parameter or two parameter acoustic. They don't care if it's elastic. They don't care if it's anisotropic. They don't care if it's inelastic. Those two algorithms, the free surface algorithm, you could see that in that derivation. It just cared about -1 and convolution, yes? And the internal is the same. The internal is more complicated to prove. There's a paper in inverse problems in 2003 where I proved that the internal multiple algorithm is independent of Earth model type. And well, that's a tremendous advantage, yes? In other words, someone comes up with the latest version of anisotropy, you think you're going to have to change your internal multiple attenuator. You don't. It doesn't have, couldn't care less about it, okay? That's very fortuitous. The other thing is, there's something very different about this inverse business than modeling. In, I think, 1993, 92, Richard Coates and I, we were together in Schlumberger in Cambridge, England, and we published a paper, or his result was he had an elastic medium with a converted wave, internal multiple, PPSP, yes, converted wave. And this algorithm, which assumes water speed, okay, that C0 is a water speed, okay? G0 is water propagator, right? Water. Water does not allow a shear wave, okay? If I said I was modeling a converted wave which had a shear component, it doesn't exist, let alone how you're going to predict it. You're not modeling it, is the point. How does this all work? I want to demystify it. When you have data, the inverse here is not, it doesn't make the multiple. It doesn't model the multiple. The multiple is already there. You don't have to make it. It's in your data. You have other data. What it looks for are combinations of data, yes, data, that will, as Bill Dragoset and I say, composite. A multiple is a composite, a combination of other events, yes? So those algorithms are just looking for combinations of events. So I'll draw one here. I thought I was going to draw it. Let me draw a simple internal. How does the algorithm predict this without knowing anything? It looks for 3 events that, and I'll say that have time. It's really vertical time they look for. They look for one event in your data and another event in your data, each which has, I'll call it, bigger time than this one. 2 larger times and 1 smaller time. And it adds the 2 larger times and subtracts the smaller and gets this. You see? It takes 2 events which have a larger time than 1. This one has a smaller time than these 2. It says add the 2 larger and subtract the smaller. That will give you this time. Yes? So if you have 3 primaries, yes? To do that, you don't have to have any information. Yes? It just looks for, so when you're doing these integrals, B1, 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 what those integrals are doing are saying, one data, make this data with deeper, make this data with shallower, make this data with deeper, deeper, shallower, deeper. And then there's an exponent here which subtracts the phase. Here it adds, here it adds. So it puts 3 datas in looking for this kind of combination. Yes? So what I'm trying to say is, it doesn't model, it doesn't make the multiple. It assumes it has the multiple. It has other data. How can other combinations of data produce this? Yes? That's what it asks. And does it? And that process requires no subsurface information. I'm giving you a cartoon of, to demystify it, yes? That's why it's multiplicative activity, yes? Okay, so Jing Wu, as part of her thesis, took a look at, okay, you say you got this theory, you published a paper in 2003. Let's actually take a look at detail of data from an inelastic medium, yes? And let's see how that internal multiple algorithm, which has water speed, Q is infinity, no absorption, how is it able to predict the correct time and approximate amplitude, yes? In other words, that G0 in that internal multiple algorithm is a water propagator with no absorption, yes? Okay, Jing Wu, look forward to your talk.
Okay, good afternoon, everyone. Next, I'd like to test and evaluate the inverse scattering series internal multiple attenuation algorithm given the Earth is inelastic. You will see this algorithm does not need any subsurface elastic or inelastic properties. Well, the inverse scattering series communicates that you can achieve every processing objective directly and without any subsurface information. As Professor Wagon described, for both free surface multiple and internal multiple, those subsurfaces not only do not care about the subsurface information, they do not care what kind of model type you have. You can change your Earth model to be acoustic, elastic, or inelastic, which will be described later. Those free surface multiple elimination algorithm and internal multiple attenuation algorithm always remain unchanged. This is what the mean of model type independence. So first, let's remind us the performance of ISS internal multiple attenuation algorithm gave a different Earth model. First, if your model is a heterogeneous acoustic, then by using a homogeneous acoustic background, Rudel and Wagland demonstrate that this ISS attenuation algorithm can predict internal multiple with exact time and approximate amplitude. Second, if the Earth is a heterogeneous elastic, then Coase and Wagland found that by using a homogeneous acoustic as background, they can effectively predict the converted internal multiples. You can see a wrong model, but a satisfying prediction result. Now in this talk, given the world is heterogeneous and elastic, where the energy of the propagating wave will be attenuated and the velocity will be dispersive, we're going to show you how this attenuator performs by using a homogeneous acoustic as its background, no absorption, no dispersion. The interest of this study comes from the reality that you are often part of the world that absorption matters. Like in the pre-salt place in deep water Gulf Mexico or in North Sea or Red Sea, the Q absorption can be significant. Then you'd like to have some confidence that even in a world with the absorption and the dispersion, you do not need to specify those properties. This algorithm will retain its effectiveness, exact time, and approximate amplitude. Next, we will test this method by showing you the analytical example and the numerical example. First, we look at this analytical part. In this session, we will give you the model. Then you can analytically express both the primary event and the internal multiple. So substituting this analytical data to that ISS attenuation algorithm, your prediction result is analytical as well. Then you can analytically compare your prediction and the actual internal multiple, see what happens. Well, here, keep in mind, we gave the model here to create the data, which is in preparation for the subsequent multiple attenuation algorithm, but that algorithm itself does not take any information about them. Okay. The ISS attenuation algorithm is designed for both multi-D Earth and 1D Earth. Here for simplicity, we just take a 1D normal incidence example to show you how it works. And here we have a two reflect model without a free surface. So there is no ghost, no free surface multiple in your data. Both source and receivers are at depths of 0 meters. We have two reflector model here, and you have velocity c and density rho, and the quality factor q here for each layer. So the velocity here you can see is frequency dependent. So it has already incorporated the influence by absorption and dispersion. Now, in this model, you will have two primary events and one first-order internal multiple event. R here is the reflection coefficient, and T here is the transmission coefficient. Now you have the data. Let's go ahead to test the ISS attenuation algorithm. This chain here shows you the workflow, how to implement the ISS attenuation algorithm. The first step, we transform the data from time domain to frequency domain. In this domain, both primary events can be expressed analytically, and both of them suffer from Q absorption and dispersion. Since velocity here is frequency dependent. Now, the second step, we map the data from frequency domain to the vertical wave number domain in preparation for the subsequent migration. One very important point here is when we do this mapping, we use a constant velocity C0 here. So the ISS attenuation algorithm take a constant acoustic model as its background, even though the actual world is absorptive and dispersive, but this algorithm does not take any information about them. Okay, after that, applying the stored migration, we can map the data further to the pseudo-depth domain in form of B1 of Z. Here, because we use a constant velocity, so the absolute depth is not accurate. But the relative depth relationship among different events return the same as the reality. For example, the first primary is generated at a shallower depth in the real world. Then in the pseudo-depth domain, it is still generated at a shallower depth in comparison with the second primary event. Next, we can take this B1 of Z to the ISS attenuation algorithm, get the predicted internal multiple. And finally, you can map the prediction to the time domain, get your final prediction result. Okay. This equation shows you the formula of ISS attenuation algorithm. You can see it has three integrals here, and each integral has one B1 of Z, which is the input data after a constant velocity migration. Now, these three B1 correspond to these three events as shown in this diagram. The integral limit here, you can see Z1 minus epsilon for the upper limit of Z2 and Z2 plus epsilon for the lower limit of Z3 makes sure that this algorithm can automatically select the events that satisfy deeper, shallow, and deeper relationship, so you can get an effective prediction result. Now go a set of calculation, you will get the predicted internal multiple B3. Let's compare this result with your actual internal multiple RM. You will have this relationship here. You can see you have two extra terms connecting B3 and the actual internal multiple. TF here is the transmission factor. It accounts for the transmission loss at an interface on and above that interface where your multiple has its downward reflection. For this example, the multiple is downward reflected at the first interface. So only the information at the first interface is involved in this expression. And the second factor is the Q absorption factor. It accounts for the transmission loss in the layers above that interface where your multiple has its downward reflection. For this example, only the first layer is involved in this expression. So now you can see, applying the ISS attenuation algorithm, a global transmission loss starting from the top and down to that interface where the downward reflection occurs will be overestimated. And it makes your prediction amplitude B3 to be smaller or approximate to the actual multiple, but the time is exact. Here for simplicity, we just show you a simple 1D normal instance with 2 reflectors. But this relationship will still be effective when you have either 1D with multi-layers or multi-D. And both TF and QF will have more complicated forms. Okay, now let me remind you again what happens here. We take the data through absorptive and dispersive Earth, but the ISS attenuation algorithm does not have that in its reference medium, and the background is kept to be a homogeneous acoustic, that simple C0. Given all that, you predict that with the exact time and approximate amplitude. This is the key message here we are investigating and like to deliver in this presentation. Okay. Next, let's further examine this method by using a numerical example for data with Q absorption. We use a 1D Earth model to generate the prestack data. Here we have 4 reflectors and 5 layers. Each layer comes with Q absorption. But again, this ISS attenuation algorithm does not take any information from this model except the data itself. Well, this test is performed during my internship at Schlumberger with Claremont. Okay, so with this model, we can generate your input data as shown in this slides. You have 4 primary events as indicated by these red arrows. And all the other events are actually the internal multiples indicated by these blue arrows. Now let's input this Q absorptive data to that to that algorithm. You can predict the internal multiple as shown in these slides. Flip back and forth. Let's focus on the events indicated by those blue arrows. You can see the time match very well, and the amplitude is weaker. So we can further pick 2 trees for a closer look, one at the 0 offset and the other at far offset. These blue lines represent your input data with Q absorption, and these green arrows are actually pointing to the internal multiple. This is your input data with Q absorption, and the red line here represents the predicted internal multiple. It's very clear to see that every multiple is predicted with exact time and approximate amplitude. Okay. In the middle of this internal multiple, you may find this small curve here. This is actually a primary event. But if you can see this red line here, this ISS attenuation algorithm never touched the primary, but just focus on working to predict the internal multiple. Now we have shown you the analytical example and the numerical example. Both come with the same conclusion: exact time and approximate amplitude. Let's draw the conclusion here. This study actually adds to the theory that the ISS attenuation algorithm is model type independent. At the end, if you apply this ISS attenuation algorithm in a world where the absorption and the dispersion matters, you're going to have confidence that the time will be exact and the amplitude will be approximate without knowing, needing, or estimating any subsurface elastic or inelastic properties. Thank you.